Hi, this is Chuck Benedict, mentor for Team 997 Spartan Robotics in Corvallis, Oregon. See if I can get centered here. Uh, I am actually recording from my relative's house in Washington, so I'm not in Corvallis, but that's okay. I've got plenty of time to do these videos, so let's get started. This video is the next one in my series about building a WPI roboRio device driver for a color sensor. And specifically, I'm really excited about this one because this one's kind of the the culmination of all the work. It's where the fun happens, where I can actually see the code actually do something. And what I'm going to do is I'm going to demonstrate to you about how you can use a device called a bus pirate to integration test with a variety of sensors and hardware without having to have the roboRio. And so the bus pirate, I talked about this a little bit on some prior videos, but it's a $30 piece of hardware that's been around for a long time. But you can still get it from Adafruit, SparkFun, a lot of different places. In fact, I don't even think the original creator is even maintaining or building new hardware. But he's built such a following and a lot of documentation that the product's still for sale and easily obtainable. Mine is 4 or 5 years old. I bought it a long time ago and thought it was cool when it was first done, but never really found a use for it until now. So I'm glad I can use it. It's really cool. So I've got I'll probably see if I can get it on camera here. So this is the bus pirate, and this is my color sensor, and I have them wired up with a rat's nest of wire jumpers. There's actually a pigtail that you can buy for the bus pirate that has a nice 10-pin plug in it that actually terminates with alligator clips like this. I just put a little header on top of the bus pirate, and I had these alligator clips, so it seems to work okay. But I would suggest if you're gonna do this, that I would buy the clips that come with it, or that can come with it already, because it just makes it a little nicer. They're, I don't know, $7 or $8. Okay, so I have the sensor already hooked up to the bus pirate. There's a schematic on the project, the GitHub project that's listed in the comments if you've never done this before. So go check that out. It's pretty easy. I2C bus is 2 wires, clock and data, and then of course you got your power, ground, and positive voltage. So it's 4 connections. It's pretty easy. Mine's already hooked up. So what I wanted to talk about, we'll come back to this. This is the Dangerous Prototypes website. They're the makers of the bus pirate. There's 2 pages on here that we're going to look at in a minute, but let's go to the code first. So here's the vision processing code, and pardon me if I'm looking around here. My relative's dogs are running around the house, and hopefully they'll behave themselves while I record this and not eat what I have on the floor. Hey, Mabel. Be nice, Mabel. Okay, so first thing, I digress. So I don't know if no one reads magazines anymore, I suppose. Mabel, don't eat my racquetball. Ah, my goodness. Sorry, I knew she would do that. It fell on the floor. Okay. So, all right, let's see if my racquetball will stay up there. Actually, I'm just going to hold it because she'll probably eat it. Sorry. So I don't know if you guys remember magazines. I used to read them, and I used to read them from back to front. I don't know why. So I'd get a new one in the mail, and I would start reading it, and I would always read it from the back, and I'd start flipping forward, not even reading articles, but sometimes I'd even read the article starting at the end, and then I worked my way backwards to the beginning. Well, we're going to do that same thing because just that's the way I think. I don't know why. Sorry if it confuses you, but it makes sense to me. So what we're going to do is we're going to start the code review. At the end, I'm going to show you the JUnit integration test first, and then I'm going to work my way backwards, sort of peel back the onion, as it were, to kind of show you how these classes interact with each other, sort of then leading back to the basics of this class. So start first with the integration test. This is the JUnit testing class that actually exercises the color sensor device driver that I talked about in the prior video. It does some basic calls to that device driver, exercises a few methods, and then ultimately it makes some calls to get the RGB color. And we're going to take a racquetball and, at the end of the video, actually run the test to show that that test actually works. So first thing we do is, of course, we have to open the device and we have to close the device. So I have another class called Integration Testmock. It's got some static methods on it. It does the initting and it does the destroying of the bus pirate device. And again, we'll go look at what those do in a minute. But on my integration test class, I've got a before class and an after class decorator that does that work for us, so that when you run this test, the first time that the test is run, and only one time because they're static, the before class and the after test called to basically set up the bus pirate so that we can use it. And I kind of like this integration test mock class, I call it a fixture, because we're kind of fixturing and setting up the conditions for the test ahead of time. This method right here, wire up bus pirate, this actually does the magic. So I'm using a mocking framework called Mockito. I've talked about that extensively in other videos. And the I2C class, this is a WPILib class for abstracting calls to the I2C bus. I use Mockito to mock up an I2C instance here. And when this is mocked, you can call methods on the I2C class now. Of course, it won't do anything. The calls will just, you'll call in and they'll return and nothing will happen. But what this allows us to do is we can mock up those calls and make them do stuff for us. So if you'll remember back a video or two ago, I talked about what the device driver actually is having to do to I2C, and very simply it reads to it and it writes from it. It does a few other things, but that's essentially all it does. So what we want to do is we want to intercept the calls that the driver is actually trying to make to the WPI roboRio I2C class, read and write, and we want to substitute in the equivalent calls to the bus pirate so that we can fake out the driver class, and so it doesn't even have to know that stuff's been sort of unplugged underneath it and new stuff's plugged in. So I use these DSL methods, these domain-specific language methods that are available within Mockito, to basically say when a call gets made to WPI I2C read using this mocked object up here, instead answer with a call to the bus pirate read method. And again, we're going to go over what these do in some detail in a second. Likewise, I do the same thing but for writing. And so with these two calls right here, anytime I make a call to the color sensor device driver class, instead of calling into WPI, I'm going to call into these bus pirate methods that I've written to do the work for us. So that's basically how this, we're able to make these integration tests work without the roboRio. There's some stuff under the covers to make this magic happen, and we'll talk about it. Okay, so let's look at some of the tests. I do a test here to see that I can initialize the sensor. There's an initial, basically the initialize is done through a constructor. So all I do is I instantiate the driver, and I just make sure that I try to catch errors, and I just make sure I can't catch anything, because in last video I talked about factoring out the use of Booleans to detect whether things worked or not, and instead throwing exceptions. So I want to basically catch those exceptions to just make sure there aren't any thrown. I test out calling enable to make sure that the power on and the AEN flags get asserted correctly. So there's a test here that does that. I make sure that I can disable it, and I talked about in a prior video, but the disable function on the code that I borrowed didn't work properly, and this is how I was able to catch it, because when I coded this up, rereading back is it enabled, it actually it was not 0, it was something else. So this test actually caught that for me, and I was able to fix it. Okay, the interesting tests. I have a test here called it can detect the color red, and I have other tests. It can detect the color blue, and it can detect the color green. So this is a test that's actually reading from the sensor and seeing that the color red that I get back is actually greater than the getting the color blue or getting the color green. And this little assert that syntax here, I kind of like it because it makes your tests a little more readable. It basically asserts that when I get the color red, that it's greater than getting the color blue and getting the color green. This is from the Hamcrest class. They wire up these little helpers for you to make this a little more English-like. So this is really all. I mean, it's pretty amazing that you can write a test seemingly this simple, and this basically fakes out needing a roboRio to run against the device driver class that we created. So let's peel back the onion a little bit and look at some of the things that actually make this work. So the mock, this is these two calls right here. Let's go look at the mock that actually makes these happen. So that's in integration Testmock. Again, in the comments, I put the link to the repository where all this code is sitting so that you can follow along later. So there's an integration Testmock class. It basically puts out a bunch of statics that allow you to just use the class as a fixture. And I mentioned to you that there's an init and a destroy that you can use to fixture up the bus pirate instance so that it's ready for testing. Really, it's not surprising. They init this bus pirate I2C TCS 34725 class. We'll go over this in a minute, but this is the class that contains the functions that call into the bus pirate to fake out the fact that we don't have a roboRio. And then in my destroy class, I basically tear down, reset the communications port, because again, I'm talking to the bus pirate over a COM port. So, we want to make sure that we clean all that stuff up and tear it down. So that's what the destroy method does. Then we have our bus pirate read and write. They're called answers in Mockito speak, because if you recall on the other, well, let's go back here. When we read, it's done through the context of an answer, and so over here in our mock, here's the answer that we've declared, and we're going to get into what is actually going on here in a bit. But we've got an answer created for reading, we've got an answer created for writing, but prior to that, we have to intercept calls to the WPI I2C read method and the write method, and here are the statics, the mocks that are set up. They're called matchers in Mockito speak. So we've set up a matcher to match for the argument signature like this. So any read that's called on the I2C class that matches an integer, any integer, another integer, and any byte buffer. And again, if we hover over, we can see what those are. The first parameter is the register address. So that's the register that we're trying to read from. The count is the number of bytes that we want to read. That's the second parameter. And then the buffer is the data that we're going to be getting back from the device. So this matcher is basically matching any read command that occurs to the WPI I2C class so that we can substitute in our own call to the bus pirate. Likewise, the matcher for the write essentially does the same thing. So the write method on the I2C class takes the register address that we're writing to, we're writing to, and it's taking a byte, or it's taking the data, the byte data that we're writing in the second parameter. So those are the matchers. Now the answers. Let's talk about, and I talked about the answer um, uh, capability on prior videos, how you sort of formulate a Mockito answer. But essentially, if you think about what's having to happen, when you make a call, let's take the read as an example. Take the read as an example. So when you call I2C mock read, or I2C read, really, when you call that, you're going to be getting back a byte buffer which is the results of the data that's filled in. So what we want to do is we want to actually almost like catch the read method as it's being called, and we want to substitute in our own return result that contains the data. It can be any data, but in this case, it's actually going to be the result from calling into the bus pirate and getting the data back from our sensor. So that's what an answer, a Mockito answer, allows you to do. It in effect substitutes in or allows you to inject in your own call for that read function, and it allows you to snag the parameters from the read function and be able to do something with the parameters or substitute the result of your own parameters if you want. And so you can see here there in these two calls, we're actually getting the arguments from the read function here. In our case, the bytes read, which is the third parameter. Sorry, that's the well, that's the number of bytes read, and the number of bytes to read, and the final parameter, the third parameter, which is number 2 because it's zero based. That's the byte buffer that we're actually going to return the results that we read into. So what is it that we're actually going to do? So we're going to call this class bus pirate I2C TCS34725, and there is a read combine method that I have created on it. If you'll recall back to the datasheet in videos past, there are 3 message formats that are defined on the TCS datasheet. There's a write message format, a read message format, and a read combined format. This method right here implements the read combined format, and that is the format where you send it the register that you're trying to read from, and then you send to it the number of bytes that you want to read, and then it gives you back those bytes. So that's what this method does, and you can see that we know what the address of the bus pirate, of the color sensor is because it's on the data sheet. So the first method from read combined takes the slave address to read from. The second command is the command code. And so, you'll remember that there were command codes that were defined in that table on the data sheet. Hex 12, I think, was the ID code, and there was a whole bunch of others. So that's what goes in here. The return buffer of the bytes that are going to be read goes in this one, and then the length of the ones to read go in here. So we'll go into this method here in a bit, but this is the call that's going to go to the bus pirate, and then we get the raw bytes back, and so this raw byte variable is a reference to the variable that was passed in to the read call in the first place. And so what we want to do is that we want to inject into it the bytes that we got back from the call to the bus pirate. So that's what this does right here. And then we rewind it back to the beginning because this is a byte buffer. So we rewind it back to the beginning so that the user that uses the results from the call to read can just read it, because I actually think in the I2C class's case, I actually think that's what they do. They give you the byte buffer back already rewound so that you can read from it. So similarly, the write answer does something conceptually similar, except it calls the write function on the bus pirate. Pretty straightforward. So that is the integration test mock fixture. Hopefully I explained that well. Again, if you got questions and I didn't explain something well, leave me comments and I'll try to do better next time or answer your comments. Okay, so let's go now backwards one more level and let's look at the I2C, the bus pirate I2C TSC34725 class, which implements the three methods on the data sheet: the write method, the read method, and the read combine method. I'm going to go down to read combine because that's the one that's the most interesting. And so let me digress a little bit. If you watch the I did 2 bit banging videos on using a terminal emulator to talk to the bus pirate and send it commands to drive the device that I had connected to the bus pirate, which is the color sensor in this case. And if you watch those videos, the commands kind of went something like this. You had to send a start bit. Actually, let me pull up the data sheet in case this is the first time you guys have actually seen the data sheet. Let me see here. Data sheet. Let me see. TCS 34725 data sheets. Oh, here we go. Sorry, bear with me. Okay, here's the data sheet. Those 3 message formats that I mentioned, I'm going to go scroll to them so that I'm not hand waving and you can actually look at what I'm talking about. Here we go. Page 12 of the data sheet. So the combined format, read protocol combined format, this is the format that method that I was on is actually going to try to implement. And you may remember that from the prior video where I was sending messages through the terminal emulator, first thing that you send out is the start bit. That's what this is. Then you send a slave address. Then you send a command. Then you send another start bit. That's another open bracket on the terminal emulator. You send a slave address again with the write with a read bit set. You send you get back your data because this is a read, that's what we're reading. And then you have to send a stop bit to actually finish the message. So that's what this is implementing. If I go now back over to my code, you can see here that I send a start bit. I send the slave address for write mode, and I send the command code. I send another start bit. I send the slave address again, but with the read bit flipped. And then I read the bytes that I expect based on the length that's been passed in, which is up here on a parameter. And then I send a stop bit. And then I happen to return true. And I actually probably going to be factoring this return true business out later and instead throw exceptions because I don't like that. Why I did it that way here, I don't know. Probably just wasn't thinking, but in any case, that's what this function's returning. Okay, so so these methods here. Now, if you think about how I might have gone about implementing this, because I was using a terminal emulator in prior videos, and I was sending this little command language that the bus pirate implements with the bracket and sending hex codes and so forth. You might think that I could do it that same way with a Java communication library class, and I send my little text, send my brackets and all that stuff. You could do it that way, but if you also remember the video when I read my 8-byte string, I actually read color sensor values off the bus pirate in the last video, and it sent an 8-byte string back with text-based ACKs and NACKs in it, and I had to reformat it, and it was kind of a mess. You'd have to do that same thing in code if you use that protocol. Nice thing is the bus pirate provides another messaging format, a binary format that makes it easier so that you don't have to do that. So let me bring up that page. So on the Dangerous Prototypes website, there's some documentation. The documentation is good. It's not great. I find it not so good because I found it kind of hard finding things. I don't know why. I guess maybe the navigation they've got is a little wonky. I don't know. That's just me. Maybe you'll find it easy. But if you find yourself trying to figure out exactly where to go, I had the same problem. I'll put links to this on the comments so that you can find it a little easier. So I mentioned this concept of a binary protocol for the bus pirate. There are actually two separate binary protocols. There is a raw bitbang protocol, and that is when you send 20 characters of nulls to the bus pirate, and when you do that, that flips the bus pirate out of its normal terminal emulation mode where you can type text commands, and it flips it into what's called raw binary or bitbang mode. And that's what this page is documenting. It's documenting for you the commands that you can do to the bus pirate in raw bitbang mode. And so, I mentioned the 20 times where you send nulls. That's actually documented right here in this first line. So sending 20 bytes of nulls, you get back from the bus pirate a response of BBIO1. So that's how you know that the bus pirate is now flipped into raw binary mode. Now, there are some things that you can do in this mode, but for the purpose of this video, the only one that you really care about is telling the bus pirate, okay, I want to now talk in I2C mode. So the way that you do that is you send 1 byte once in this raw binary mode. You send 1 byte and you send, I don't know why my thing is doing this, you send that 1 byte and that flips it into binary mode. That's it. And then, so I'm going to click here to go into I2C binary mode, because this is the mode into which you emulate doing the things that you do in the terminal emulator, but you would do it using this binary protocol. So for example, putting the left bracket in the terminal emulator, the equivalent of doing that in this mode is sending a byte with this bit set. Likewise, sending a stop bit, you would send a byte with these 2 bits set. Telling it to do a read, you would send this command. Now, what I found myself when I was coding this up, what I found myself getting confused, and again, maybe it was just me because I'm slow. When you look at the datasheet, these are the data streams that you're trying to send to your color sensor. But remember, you have a bus pirate sitting in between your workstation and your color sensor. It's not like the color sensor, it's not like you have an I2C bus sitting on your Mac and you're directly sending I2C commands to the device plugged into your Mac. You actually have a bus pirate plugged into your workstation, and you have your color sensor plugged into the bus pirate. So in order to send I2C commands to your sensor, you're actually commanding the bus pirate to do that on your behalf. So you're not writing code directly to I2C, you're actually writing code to the bus pirate, if that makes sense. So separate in your mind that you have these 2 different things going on, so that when you want to send stuff to I2C, you have to formulate the commands to the bus pirate in order to do that on your behalf. And so that is what this page is documenting. It's documenting those commands for you for the bus pirate to actually do that on your behalf. So down here below, let's look at the start bit, because that's one of the easiest things. Send an I2C start bit, and the bus pirate responds back with hex 1, essentially confirming that it did that for you. That's not to be confused with an acknowledgement, an I2C acknowledgement. It's similar, but it actually isn't. It is the bus pirate acknowledging to you that, yes, I obeyed your command of sending the start bit to your device. Okay, so let's go back to the code now. Let's look at send start bit. Let's look at what that's actually doing. So I'm going to go back now. Again, I'm going back up the food chain one. I don't know why my go to definition. No. Okay, thought I did that. So the Bus Pirate I2C TCS34725 class inherits another class called Bus Pirate I2C. Now, I'm going to probably, these are all sitting in my test directory right now, but these are so useful and they're not specific to running this particular test. They actually would be useful if you were to write your own test against simulated I2C stuff that you might want to actually, like you might actually want to integration test some hardware or some assemblies that you've got. In our case, we have a ball sorter subassembly that we're building. So I could foresee us taking a couple of bus pirates and plugging it into a workstation and plugging those into the sensors that we have on our subassembly and actually trying to run some integration tests against that assembly so that we don't actually have to have the roboRio plugged in. We can actually just test our assembly. Hey, Mabel, we can test our assembly standalone. So these two classes that I'm going to show you, this Bus Pirate I2C and Bus Pirate classes, should be probably pulled out of here and a library developed to where you can use the Bus Pirate to test your subassemblies without a roboRio. So send start bit, what does it do? Well, it just simply calls this method that I've got here called common command, because there's a whole bunch of, I send one bit and I get back a response from the Bus Pirate. So I've sort of combined all of those things together. And so let's go look at what common command does. Here's common command. It takes the command, and again, this is the Bus Pirate I2C binary mode command, not commands to the sensor. Got to keep that straight in your head. So this takes the command, it puts it into the send buffer, and it basically writes out to the serial port. And I'm using it's called PureCom, I think. I'm using a open source Java serial library to do this. And actually, this serial library I'm using is nice because it is a pure Java library. It doesn't rely on JNI and stuff like that, which is really nice. I didn't find many of them out there, so you don't have to drag down from wherever JNI for your specific workstation. I happen to be on a Mac. I actually developed this code on a Windows workstation, and very nicely, I was able to just run a build on the Mac, and it just worked as if I was, running on Windows. So again, very, very nice. So here's my write method out to the serial port. So then I read back the result from the serial port, and if you remember on the Bus Pirate documentation, I get back a response of hex 1 if things worked. So that's what I am attempting to read back here. And then so here you can see I'm checking whether or not I get back hex 1, and if I don't, I throw an exception. So, so sending start bits and stop bits and things like that, they're all called here in this function right here. Okay, so okay, sorry, I had to check on my dog. Finally, then the final so this class, this Bus Pirate I2C class, it implements the features required for interacting with the Bus Pirate I2C binary mode. Also, then I have a final class called just Bus Pirate, and this is a class that deals with interacting with the Bus Pirate in its raw mode. So things like scanning all of your COM ports to try to find a Bus Pirate. So that's one thing that this class does. Flipping the Bus Pirate into I2C mode. So opening the COM port, closing the COM port. So that's what this high-level Bus Pirate class does for you. I'm not going to go into these things because this video is getting kind of long. But I think sort of understanding how this is laid out, You can go in at your leisure if you want to explore this stuff a little more. What I wanted to do is I actually wanted to run a test because, hey, this is the fun part, and actually see this in action. So here's my ball. I got my bus pirate and my sensor off camera. I'm not going to really show that. But what I'm going to do is I'm going to run the test suite, and we're going to take a look at the results. So here's my ball. I'm going to run the test. I'm going to hold my ball over the color sensor, and we're going to watch what happens. So the first thing it does, you can see it actually scanning the ports, which is kind of handy. And here's all my tests. Now it says test fail, and the reason that it says test fail is because you remember I had a red, a green, and a blue test, and I had one ball, and of course I obviously wasn't. Yes, Mabel, I know you're down there. Obviously, I wasn't going to be flipping the balls back and forth as the test was running. But if I scroll up here and I look at the test of it should see red. Let me see if I can find it. Yes, there it is right there, actually. It can detect the color red, and you can see that that one passed. However, the colors blue and green, okay, yeah, it can detect the color blue, that one failed, which I expect, and it can detect the color green, that one failed. So you can see these tests are actually running against the bus pirate. And I mentioned in the other video I had a verbose flag on the constructor of the driver class that would spew out stuff to the console, and this is an example of what it's spewed out. So you can see it's actually telling you what it's reading and writing on the bus, which is kind of nice for diagnostic purposes. So that's really kind of it. I mean, there's some other nuances that I won't show you. I'll mention them. So when you build this project, it may well be that you don't have a bus pirate and you don't have this thing plugged in. So obviously, you don't want these tests to run if that's the case. So the way I have this rigged up is when you run test, it actually enumerates all of your COM ports like it did here. And if it finds one, it runs the integration test just as I've run here. If it doesn't find one, it skips all of the integration tests. And you can actually see on the console, you can see where, hey, I didn't find a bus pirate. That's fine. I'm going to skip, it can detect red, blue, green, all that stuff. And you can see that they're skipped. And then it allows you to build the project as normal so that you get the binary, which is cool. So long video, sorry for the length, lots to cover here. In the final video, I am actually going to hook this thing up to a roboRio, and we're going to see if all of this work netted us a final working product right out of the gate. Thanks for watching.